Hi everyone, in this video we are going to predict the favorability of a reaction based solely on the signs of delta H and delta S. All right? And this is only going to give you a rough idea of should we elevate temperatures to make a reaction favorable, or lower temperatures to make it favorable, or is it just going to be favorable under all conditions or no conditions? So we're not going to have an exact answer at the end of this, but it's going to be a useful predicting tool for us when we don't have the numbers available for a process. All right. So as always, we're going to start with the Gibbs free energy equation, delta G equals delta H minus T delta S. All right. And what we're going to do is we're just going to make ourselves a table of delta H, possible signs of delta H and possible signs of delta S, and see what the consequence is for the sign of delta G. All right. There are four possible combinations: negative plus, plus minus, plus plus, and minus minus. Those are just the four possible combinations you could have of the signs for the two terms. All right. And so let's work through these one by one. So for negative positive, that means that this term, the delta H term, would be negative. Now the positive delta S term here has a negative number out in front. We don't have to worry about the temperature, right? Because the temperature is always going to be in Kelvin. That minus sign, so it's always going to be positive. That minus sign applies to the whole term, so these numbers are both positives. So now we're going to have, right, that's positive. So the entire term here is going to be negative. So you're going to have a negative number plus a negative number, and that's always got to add up to a negative number, right? There's no way to have two negative numbers add to each other, not multiply, add. If they are added together, they have to add up to a negative number. So that means that this reaction is favorable always, all right? There's no temperature at which this reaction, this type of reaction, would be unfavorable, okay? Another trick that can be really useful here, if you're having trouble with the signs, is to rewrite the equation as delta G naught equals delta H plus negative T delta S. And we'll try it this way on the next one. So if you have a positive delta H and a negative delta S here, well, that means that you have a negative times a positive times a negative. That means this entire term is now positive. So you have a positive plus a positive. Positive plus a positive has to add up to be a positive number. There's no other way for that to happen. So this is positive, and it's going to be unfavorable always. In other words, at all temperatures. Okay? What about for our third combination? And I'm going to stick with my slightly rewritten version of the equation from here. So if we have a positive delta H and a positive delta S, that's times a positive delta, times a positive temperature. Now you've got a negative sign out in front of that. That makes this whole term come out to be negative, right? So now we've got to think, what makes one term bigger than the other, right? Because that's what's going to determine. If this is like positive 10, this is negative 5, it's going to add up to be a positive 5, right? And the way that you make, so the relative size of these two terms, the absolute value of each of these terms is what matters now. And the way that you make this favorable, in other words, if you want the delta G to come out to be negative for it to be favorable, you make the temperature as high as you can. That's the only thing you can adjust here, right? The delta H and the delta S are determined by the reaction. Those don't change. But you could, as the experimenter, raise the temperature, and that would make this negative term bigger and bigger and bigger. And at some point, the absolute value of the negative term would be larger than the positive term. And then when you added the two together, you would get a negative number, right? So that means that this reaction is going to be, the delta G will be favorable, or the delta G will be negative, making it favorable at high temperature, and it will be positive, unfavorable, at low temperature. Okay? And you can do the same analysis with negative, negative, and you get basically the same thing, except backwards, right? You get that it's positive and unfavorable at high temperature, that it is negative and favorable at low temperatures, all right? We are going to use a couple of terms for this, namely that when, for these two down here where they are favorable sometimes depending on the temperature, if the delta H matches the sign of the delta H in the always favorable case, we're going to call this enthalpically driven. Okay, and why would that be? That's because when this term is large, in other words, at low temperature, if this term is large compared to the T delta S term, that the reaction, the reason it's favorable is because of the enthalpy. So we call that an enthalpically driven process. If the delta S is positive, matching that of the always favorable case, we're going to call this process entropically driven. And that's because it is the minus T delta S term that's making this reaction favorable. In other words, at high temperature, when T delta S is large, then we get a negative delta G of favorable reaction. Okay? So when you do these, again, if we just know the signs, we're going to write the Gibbs free energy equation. It can be really helpful to rewrite it with a plus in the middle and then that minus attached to the T delta S term. We're going to put the signs in there and think about what does that do to the size of to the term. And then we're going to ask ourselves, how would the temperature affect the relative size of the delta H and the minus T delta S term? And from that analysis, we're going to be able to predict if a reaction is favorable always, never, at high temperature or at low temperature.